Okay, so today we talk about the display, just to have an idea of what is the technology at the basis of the operation of display. Of course, as I mentioned at the beginning, if you look at the bill of material of an expensive smartphone, then you should see this is the bill of material, which is the cost of all the components. The display is the most expensive one. Okay, this is the processor, which is probably the second most expensive one, but then the display is let's say first or second. In the iPhone 5S is a little less expensive, but just a little. For the larger the phone, of course, the more expensive the display is, and so it is a critical component, and it is also the one that consumes the most energy. So it's most responsible for the battery life. So let's see the technology at the basis of the display. But first we need to look at the make some considerations on the visible light. Is it working? I think it is, yeah. On the visible light. Okay, the visible light goes to from red to blue, and the wavelength varies from the longest wavelength of 780 nanometers for the red light, below at higher wavelength, which means at lower frequencies we have infrared radiation, and the visible light goes up to a wavelength of 380 nanometers, so which is the highest, which corresponds to the highest frequency of the light, and above it we have the ultraviolet range. Now I must just mention a few relationships that you probably already know between the wavelength, the frequency, and the energy of the light. And the relationship is the following. The frequency is related to the wavelength through this relationship, where lambda is the wavelength of the electromagnetic radiation, c is the so-called speed of light, is the propagation velocity of the electromagnetic radiation, and it's a universal constant. It is 3 times 10 to the 8 meters per second. Okay? And the ratio of c to lambda is the frequency of the light. Then from the frequency we can know the energy of each single photon. As you know, light consists of photons. There's this very well-known wave-particle duality in physics. We can see light as a wave, or we can see light as a bunch of photons moving at a velocity equal to c. And each photon, which is a particle moving at the velocity of light and carrying an energy corresponding to the frequency of the electromagnetic radiation. So this energy is equal to Planck's constant, which is denoted by h, times the frequency. So this h is Planck's constant and is something like 6.64 times 10 to the minus 34 joule times second. Okay, the unit of measure is an energy times a time. Okay, this is the energy of a photon. Let's write it explicitly, associated to F. As depending on the frequency of the electromagnetic radiation, we have a change of the energy of the photon. Okay, when we change the frequency, the speed of the photon does not change, but the energy of the photon changes, and it is rigorously proportional to the frequency. So, if we want to know the energy of a photon corresponding to a given wavelength, we just have to substitute this expression for F in the formula on the right, and we have something like E is equal to CH over lambda. Okay? So, for example, just to have an idea of the energies involved, if lambda is 780 nanometers, and we substitute these numbers in this expression, we have an energy that is 2.55 times 10 to the minus 19 joule. So this is the energy of a photon corresponding to this wavelength. Okay? Okay. The other thing that I need to add is that we typically do not use this unit of measure for energy of photons, and also for energy of electrons in general, for energy of small particles. We do not use this this unit of measure because the numbers become extremely small, but we use a unit of measure which is called EV, which stands for electron volt. Which is 1 electron charge times 1 volt. And 1 electron charge is 1.6 times 10 to the minus 19 times 10 to the minus 19 coulomb times 1 volt, and so we have 1.6 times 10 to the minus 19 coulomb times volt, and 1 coulomb times 1 volt is equal to 1 joule. So 1 EV is equal to 1.6 times 10 to the minus 19 joule. So by using these units of measure, you see that the energy of a photon in this case becomes a little bit larger than 1 EV. And if we do the calculation precisely, is 1.59 EV. Okay? So the electron volt is a convenient unit of measure for photons, energies, and for also electrons, energies, and small particles, energies in general. Okay? So if we consider the other end of the visible light, the blue, the deep blue, we have of course, the highest energy in the visible light, we just have to use the same formula. Okay, that's extremely easy. Then we have to change the unit of measure in order to write the energy in electron volts, and we end up with 3.27 eV. So this is red and this is blue. So the energy of a photon, let me just stress this aspect, in the visible light is between 1.59 electron volts and 3.27 electron volts. Okay? So first point I want to stress, because of course if we want to generate light, we need to generate photons with this energy, with an energy in this range. Okay? Now, the simplest way to generate light with a solid state device is by using an LED. Okay? LED. LED stands for light emitting diode, and of course now it's an extremely common component. Okay, not just for small lights such as this on the microphone, but of course the displays of computers, of smartphones are typically based on LEDs, and very recently also let's say lighting modules and also lights for cars. So it's become, especially in the last 10 years, a really huge industry. And essentially a light emitting diode is a diode. Okay? It is a diode that has the specific property of emitting light when it is in the on state. Okay, let me just describe what is the process. You know the operation of a p-n junction. When a p-n junction is biased in the on state, you know that we have the simultaneous diffusions of holes in the n regions and of electrons in the p region. So we have, in this situation, holes. Let me show them in blue, that diffuse to the n region, and we have electrons, of which I have many in the n region, that diffuse in the p region. I don't want to discuss now the operation of a p-n junction, but you remember, when the p-n junction is in the on state, the barrier for electron flow between the p region and for electron and hole flow between the p region and the n region is very small, and therefore we have diffusion of both types of carriers. Once typically one can typically plot two different graphs. One is two different lines. What is the energy, the potential energy for electrons from the p region to the n region, which sometimes is called conduction band. and one also plots the inverse of the potential energy for, so this is the potential energy for electrons. One also plots the inverse not the inverse, the opposite. The opposite, so it is -1 times the potential energy for holes, which is called sometimes the valence band. Okay. This is x, and this is the energy, and x is the longitudinal coordinate. So what happens is that actually you have electrons here that can, let's say, go over the barrier represented by the P region and diffuse in the P region, and you have holes. The illustration for holes is reversed because I'm plotting as a -1. The holes see a barrier, which is this one, because I have reversed the profile of the potential energy for holes. The holes that have a positive charge can now diffuse into the end region. Now, what happens here is that after this diffusion, we have a recombination. In this region, we have several injected electrons and a majority of holes, and then the electrons recombine with the hole, which means the electron occupy a state close to a silicon atom, which was empty, okay, which of course corresponds to a hole. When the electron recombines with the hole, we have that the electron vanishes, the hole vanishes, and during this recombination some energy is emitted. And in the light-emitting LEDs, the emitted energy is emitted as a photon. So it is emitted in terms of light. So we have in LEDs this recombination and the emission of a photon. Okay, and the energy of the photon, energy of the emitted photon, is the difference between the energy of the electron and the energy of the hole with which the electron has recombined. Okay, and is essentially identical to the difference between this potential energy for electrons and minus the potential energy for holes. This is, in semiconductors, is typically called energy gap. So the energy gap is the energy that is lost during a recombination of an electron with a hole, and in light-emitting diodes this energy is transformed into one photon. Okay? So in order to have the emission of photons, we need to have current, because we need to have this diffusion of electrons and holes at the same time. Okay? In order for this to happen, we need to have the proper material. For example, silicon does not work. Okay? In the case of silicon, we do not have a light-emitting diode because of the due to the property of the material. During a recombination, we have the emission of a mechanical vibration and not of a phonon. So we really need to choose the proper material in order to obtain light. Okay? So silicon does not emit light. It emits a mechanical vibration, which is essentially heat. So this energy which disappears during a recombination becomes heat, okay, vibration of the atoms of silicon. There are other material systems in which with which we can obtain light, and of course we can obtain light of different colors depending on this energy gap, because depending on the energy gap we have different energies of the emitted photons, which correspond to different wavelengths, which of course correspond to different colors. Okay. For example, three materials that work pretty well in order to have light are gallium arsenide, gallium arsenide has a chemical formula which is GaAs. Ga is the symbol of gallium and As is the symbol of arsenide, and it emits light, and actually it's light in the infrared, because the energy gap of gallium arsenide is 1.43 eV. So with gallium arsenide we do not have emission in the visible light. We have emission at a lower energy, which means in the infrared region. But for example, with gallium phosphide, and the symbol is Ga for gallium and P for phosphor, we have emission of light in the more or less in the green, because the energy gap is no, sorry, I need to write the energy gap. The energy gap is 2.26 eV. Okay, so if you remember, the red was 1.59 eV. So 1.43 is below the red, and which means infrared. 2.26 is of course above the red, but is of course below the blue. It's in the green part. Let me just use the... We are here. Okay, at about here, because we are below the blue. The blue is at 3.27 eV. Okay, and the nice thing is that if we use a mix of arsenide and phosphide, a material which is called gallium arsenide phosphide, we use let me write it in this way. We use a fraction X of arsenide and a fraction P of phosphorus. We have a material which has a gap in the middle between 1.43, the gallium arsenide gap, and 2.26, the gallium phosphide gap. Okay, so we can obtain all the frequencies in the middle. We can obtain, for example, the red. We can obtain, for example, the green by adjusting the molar fraction of arsenide and of phosphor. Okay. and also this material, of course, emits light. If we want the blue, we need to use gallium nitride. The symbol is GaN, N for nitrogen, and for gallium nitride the gap is 3.4. So it's basically blue. It's just a bit above blue. I don't know if you follow the tech news. The blue LED is the gallium nitride LED. It's something that has become pretty popular in the last 10 years. Okay, so an LED, if we look at its basic properties, it's just a diode made of a semiconductor which is capable of emitting light. By choosing the proper semiconductor and by adjusting the molar fractions of the material, we can emit light at any frequency we want. Okay. Now, okay, this is just the basic. Then the point is that, as you probably know, LEDs were demonstrated experimentally in the 60s, and only now we start seeing them everywhere. Okay, and what's the reason for such for such a delay? The reason is that in all these last 50 years there has been a lot of optimization from the point of view of the type of material, from the point of view of the structure of the diode, because many more materials than the one that I've just shown you are used in a commercial LED now. And everything has been done in order to optimize the structure so that in practice for almost any, I would not say any, for a large part of electrons and holes that diffuse during the operation of the diode, we have a generation of a photon. Okay? So in order to optimize this process and having a good efficiency of the LED, there has been a lot of investment in optimization. But the basic principle of operation remains the one that I have described. Now, where do we go from that? Okay, we need to add, let's say, something different, because of course now we have an idea of how we can have blue LEDs, red LEDs, and green LEDs. The point is that we typically need, we very often need white LEDs. How do we get them? Okay, in order to have white LEDs, there are basically three options. Okay. One option is to have let's say, sum three different colors. Okay. For example, as you can imagine, to have a blue LED, a red LED, and a green LED at the same time. Okay. So, and this is actually an option that is used: blue LED plus green LED plus red LED. Okay. By adjusting the intensity of the three different LEDs, we can obtain a good white, or at least, let's say, a type of light which is detected by our eye as a white. Because that is a white. A white is something that we see as a white. There is no particular, let's say, combination of frequencies, or it's something that is perceived as a white. And this is one possibility. which is not very common because typically there's a problem with aging. Different LEDs do not age at the same time, so you have a white now, and then after 1 year your white is become maybe typically, for example, what happens is that yeah, it depends on the technology, but one of the 3 types of color changes in intensity and ages more than the other, and then the combination of the 3 colors does not give you a white anymore, but something which is closer to a combination of 2 of the colors. Okay, so this has a problem, let's say, with aging. It is used, but I mean not so often because of this problem. The other option, which is common also because it's relatively simple, is to use a near UV plus an RGB phosphor. Okay. So near UV LED, did not write LED. So a LED which has an emission over the blue, almost over the blue, between at the very end of the blue. Okay, and then an RGB phosphor. What is a phosphor? A phosphor is a fluorescent material which receives light in the UV frequency, and then emits light at a smaller frequency, at a lower energy. So you have something like UV here, then you have a red phosphorus that emits light in the red, a blue phosphorus that emits light in the blue, and a green phosphorus that emits light in the green. Okay, let me also write this word because fluorescent. Material. A fluorescent material is a material which is able to absorb light at a certain frequency and then re-emit light at a much smaller frequency, not exactly much smaller. And of course, the 3 different types of phosphors must be, let's say, sized in a way as to obtain a good white. Okay. That is pretty common, and actually is the type of technology that is used in the fluorescent lights. The neon lights are fluorescent light because we have the discharge of the neon, which is in the range of UV light, and then there is the coating, the white coating of the lamp, which absorbs the UV light and then emits light in the red, in the green, and in the blue with the proper combination to give an almost white light. Okay, so the fluorescent lamp, the neon lamp, and also the low energy small fluorescent light work with this exactly same principle of operation. Okay, and then the other option, which is also quite common, is to have a blue LED plus a yellow phosphor. So you have this blue light, then you have a phosphor which re-emits light in the yellow, and the combination of blue plus yellow is perceived by the eye as a white. Okay, it's not a fantastic white, but it is a relatively good white. Okay. So these are the three main options in order to have white LEDs. What's the use of white LEDs? The use of white LEDs typically is for lighting at home, for lighting, for example, in the car, but also for lighting for the backlighting of the display of a smartphone. Okay, so you need these types of white LEDs. Okay, the other thing that I would like to add now is the fact that the voltage that one has to apply to the light emitting diodes in order to put them in the on state is typically close to the energy gap. So, for example, in silicon you have a V gamma, a non voltage of 0.6 volts. But if you want to have a gallium nitride LED, since the energy gap of gallium nitride is much larger, is 3 times the energy gap of silicon, and since you want, let's say, an intense light, you typically have to apply 4 to 5 volts to the LED. Okay, so you typically need 4 to 5 volts in order to put the LED in the on state and to have a significant light. Okay, and of course we already discussed this issue on a device as a phone. You have a lithium-ion battery with a voltage of 3 volts, and you need to increase the voltage with the proper DC-DC converter in order to have the voltage which is, let's say, adequate to drive the LED. Okay, now okay, just one thing before we make a break. Talking about LEDs, we need to mention another type of LEDs which have become quite common in the last few years, really, which are the organic LEDs. The OLEDs. This O stands for organic LEDs. So the principle of operation of an organic LED is identical to the principle of operation of an LED. The only difference is that the material is different. We do not use a normal semiconductor, a crystalline semiconductor for an organic LED, but we use typically organic molecules, and this is the reason for the name. So basically we have 2 different layers. We have an organic layer that is p-type. Then we have an organic layer that behaves as an n-type semiconductor, so that we have a p-n junction. So the principle of operation is very similar. There are large differences in the way in the fabrication procedure. Okay, just for the sake of using the proper names, the organic layer which behaves as p-type is called, in the case of organic semiconductors, Hall transport layer, which is called HTL, and the organic layer which is n-type is called electron transport layer. Okay. So the huge advantage and the reason why organic LEDs are used is because, especially for large surfaces, they are in principle at least much less expensive than normal LEDs. Because for a normal LED I need to have a crystalline semiconductor, so typically I have to start from a wafer, and a wafer of gallium nitride or a wafer of gallium arsenide is typically much more expensive than a wafer of silicon. But also silicon is expensive. Okay? For an organic LED, these two layers are obtained by printing. They are just printing, we just print them on a plastic foil. Okay? So the fabrication is, at least in principle, much cheaper, and one can have large dimensions for example, for a display. That would be very well welcome. In order, the other advantage is that with an organic LED we can use transparent electrode, and typically the situation is like this. We have one electrode here. We want to discuss displays today, so just think in terms of a display. It's useful to have a transparent electrode because we can have one electrode here made of a metal, and then we can have a transparent electrode here. Let me just color it with a different color. And then on top of the transparent electrode we can have a glass or a transparent plastic. So this is the transparent electrode. The nice part is that you have current from this the transparent electrode to the electrode. Then when you have this current here, you generate the photons, and the photons can directly go out from the glass. So you have passing through the transparent electrode. So you can have a nice flat LED, which is very interesting for a flat display. Okay. The transparent electrode can be done with many different types of material. Let me just stress a couple of things. The most common one is called ITO. ITO stands for indium tin oxide. In Italian would be ossido di stagno e indio. Tin is stagno in Italian. And that is the most common way of using it. By the way, just this indium tin oxide is also used very often for solar cells, because also for solar cells you typically need a transparent electrode, because also solar cell is basically a diode. No? You need a transparent electrode. And because a solar cell, by the way, works exactly at the opposite of an LED. You absorb light and you generate a current. So it's really the opposite. Still, you need a glass, a transparent electrode, in order to allow the photon to enter the semiconductor, enter the PN junction. So typically indium tin oxide, most recently, but not yet in commercial product, also graphene is used as a transparent electrode. Okay? Because graphene is a material which is conducting, but is also practically transparent. Okay? The transparent electrodes are not easy to find, because typically a metal is not transparent. You need something which is conducting, but at the same time is transparent. A metal does not work. And what works are typically some special oxides, such as the ITO. Okay. Now, what is this organic material that is used for the LEDs? So just to mention the two different categories at least. There are two different types of LED. One that is based on small molecules. So organic layer material, and one which is based on polymer, and polymers are large molecules. Okay, there are classes of small molecules. Sometimes these are called small molecules OLEDs, and the one based on polymer are called polymer LEDs. Polymer OLEDs. Okay, so there are two different classes. Okay, so this is the basic device. Of course, from the basic device to the display, there's something to discuss. But we stop here for a few minutes.